Hello, this video is going to derive the heat diffusion equation on a Cartesian coordinate. So here we have our heat block, and we're going to follow the balance that there's energy in minus energy out plus energy generated is going to equal energy stored. And so if we start with just this first block here of the energy in minus the energy out, we have some sort of heat flow. If we focus first just on the x direction, so we have heat flow going in the x direction, and then we have heat flow coming out in the x direction as well. And the difference between the in and the out is that there is going to be a change in the direction x, the movement in the x direction. And so if we were just to first approximate the flow going out, the linear approximation would be the flow going in plus the heat flux with respect to x times the actual movement in the x direction. And so this is the energy going out, and then this would be the energy going in. And so if we start with that first section, energy in minus energy out, we would have the heat flow going in minus this linear approximation and these two values would cancel out, leaving us with negative change in heat flux with respect to x times the movement in the x direction. And so we can likewise do this for all of the x's, so in the y and the z direction, and that would get us the same thing, just with the y and z, so it'd be negative dqy over dy and negative dqc over dz with respect to dz. And so these two would just follow the same logic as this one. And then so now that we have these, we want to approximate what the heat flow in a direction is. So again, just focusing on the x direction, this would be approximated to be the heat flux in the x direction times the area. So the heat flux, according to Fourier's law, would be negative times the thermal conductivity constant times the change in temperature with respect to x. This would account for the heat flux in the x direction. And then as for the area, if we look here, the area would be this here, which would just be dy times dz. So this would be the area. And likewise, we can do that for the x or the y and z direction as well. So again, negative thermal conductivity times the change in temperature with respect to y, and then this would just be dx and dz because it would be this area here. And then we can do that for the z direction as well, so negative thermal conductivity times the change in temperature with respect to z times, and then this will be dx dy because this will be this area back here. And so now what we can do is we can plug these three equations in for this equation, and that will finish out our energy in minus energy out. And so these three equations up here have the negative sign. These thermal conductivities have the negative sign as well, and so those will cancel, giving us a positive, and they all have a K value, so we'll divide them all by K. And so what that's going to leave us with is that's going to leave us with the change in temperature over with respect to x, dx, dy, dz, and this will be the second derivative. And that will be all the values. So second derivative in the y direction of the change in temperature with respect to y times dx, dy, dz. And then lastly we have the z direction, so second derivative with respect to z of the change in temperature with respect to z times dx, dy, dz. And then these all have a K value out front. And so this is our energy in minus energy out. So our energy generated would just be the heat flow that is generated. So this is our energy generated. That's going to be the heat flow that is generated times the volume. So that's going to be dx, dy, dz. And that's all we have for energy generated. And then energy stored is equal to the density times the heat capacity times the volume, or times the change in temperature with respect to time times the volume, so dx, dy, dz. So those are our three energy sections. So if we look at them, they all have dx, dy, dz, so those will all cancel out. And then we'll be left with the second derivative of temperature with respect to x plus the second derivative of temperature with respect to y plus the second derivative with respect to, or second derivative of temperature with respect to z. And so that's our energy in minus energy out. And then we have the energy generated, so plus the flow generated, plus divided by this K value, because we would divide all of these by the K value, which gets rid of it for this, but now puts the thermal conductivity underneath the flow generated, is equal to the energy stored. So we'll have the density times the heat capacity divided by, again, the thermal conductivity value K times the change in temperature with respect to time. And so if we remember, thermal diffusivity is defined as alpha, which is equal to K divided by density times heat capacity. So this value here is just 1 divided by the thermal diffusivity. So that gives our final heat diffusion equation, which is the second derivative of temperature with respect to x plus the second derivative of temperature with respect to y plus the second derivative of temperature with respect to z plus the heat generated over the thermal conductivity is equal to 1 over alpha, the thermal diffusivity, times the derivative of temperature with respect to time, and that is our final equation.